Right, now we're on to angular momentum. This gets a little bit more heavy, but hold tight. We start with the quantum mechanical. In quantum mechanics, the angular momentum operators are L of x, L of y, L of z. Now, P of x is which is the classical momentum operator, is easily transformed to a quantum state with the minus h bar operating minus I h bar operating on the derivative with respect to x, and then we can do the same for the y and the z. Now, for position components, we use the rule that the operator x hat is simply the act of multiplying x with similar rules for y and z. Applying these rules to the z component of angular momentum here, then with similar expressions for L of x, L on x and L on y here, and we substitute these operators, our quantum mechanical operators, and corresponding expressions for px, py, then we get this for our L of x and this for our L of y. These equations are the starting point for the quantum theory of angular momentum. Now, a quick note: spherical coordinates, we should probably all know those by now, and they're here anyway for clarity. Now, the expressions for L of x, L of y in spherical coordinates are very complicated, so we won't write them down. But it's possible for us to show that L of z equals minus I h bar d by d phi. And for quantization of L of z, the general allowed values of an observable O are the eigenvalues of the corresponding quantum mechanical operator O hat. We wish to find the allowed values of the angular momentum operator Lz, and we can do this by finding the eigenvalues of L hat z. So L hat of z takes the form here, which is just this basic operator where L of z is always going to be in relation to the azimuthal. So where A alpha is a constant operator, minus I h bar over the derivative with respect to phi, does not affect the r and theta coordinates, so we can assume that the eigenfunctions of the form psi r theta phi equals g of r theta and f of phi. From the equation before, we have this where the alpha phi of x, which has a general solution given here from basic differential equations and solutions, which we'll get onto at a later point. I'll have a whole new playlist on those differential equations, and we're going some fluid mechanics, pure mathematics proofs, and all kinds of stuff. So please do subscribe, and there's a lot more to come. Anyway, where A is a constant and M equals alpha over h bar, to demonstrate using f of phi equals e to the I m phi, where the operator is operating on this, we get this. So for f of phi is an eigenfunction of Lz with eigenvalues m h bar, and from symmetry we know this. The psi is basically here going around the axes. Say this is a sphere of some kind, and this is going around the axis, so phi plus 2 pi will get us back to phi because we're going around in a circle. But anyway, we require that a to e to the im phi plus 2 pi equals a to the im phi, which gives us this equation here, and from Euler's identity, which is satisfied if m is an integer. So m equals this. This is often known as the magnetic quantum number or azimuthal quantum number. I call it the azimuthal quantum number, not just because I'm a mathematician, because it's just better. And to be honest, there's no confusion. Anyway, normalization and orthogonality of eigenfunctions. If it is conventional to choose a constant a to be 1 over 2 1 over the root of 2 pi. An eigenfunction of L of z with angular quantum number m can be written in this form. The choice of A assumes that it's normalizable. Two different eigenfunctions, f of m of phi and f of n, must obey this law here, for m not equals n, so are orthogonal, which would be Kronecker delta. Although L sub x and L sub y are hard to write down, we are free to choose any direction for the z-axis, and no matter what direction is chosen, we will always find z component of angular momentum is m h bar. This means angular momentum components taken along any direction in space can only have 0 plus minus h plus minus 2h. It follows the possible values of L sub x and L sub y are 0, h by the reasoning just given. So all three operators Lx, Ly, or z have the same set of eigen values by what we said before about moving the axes, because it doesn't really matter where you put the axes itself. It's like in general relativity, it's an actual phenomenon in physics should not be subject to the coordinate system in which it's observed. So the same principle here applies. So just because if we change the coordinates, I mean, we can plonk the coordinates or axes in any directions we choose, and that's exactly what we've done here to simplify the mathematics greatly. Otherwise we'll be dealing with cotangents and all kinds of odd, complicated stuff. Anyway, the classical expression for the rotational energy of a rigid body rotating around an axis is here. L squared, uppercase L squared over 2I, where I is the moment of inertia. We therefore discuss quantization of L squared. The quantum mechanical operator L squared is given here as a sum of Lx, Ly, and Lz squareds. Eigenvalues of L squared are here, which we just come out and state them, and we'll come across this as well in the atomic physics lectures and in these quantum mechanics playlists as well. So it's L plus 1 h bar, where L is the non-negative integer, L equals 0, 1, 2, 3, and so on. So the first few values of L squared are here, 0, 2 h bar squared, 6 h bar squared, 12 h bar squared, where L and h bar, where L is the orbital angular momentum quantum number. In direct notation it's this. Yeah, so L of z is acting upon this, and we get these as an output. And the m, the azimuthal quantum number, multiplied by the Planck's constant, h bar Planck's constant. H bar Planck's constant is basically h over 2 pi. Yeah. Anyway, please do subscribe and like, and we'll keep these coming. Thank you.